Okay, so welcome to the second week's live session for the NPTEL course Fluid Dynamics for Astrophysics. I'm Supratha. I'm a PhD student and a PMRF scholar, and I'll be conducting these sessions. And this is live sessions held on Fridays, 7 p.m. to 9 p.m. And today we'll be covering, first of all, we'll be revising whatever was covered in the lectures for this week. And if you have any questions from the material, then please stop me and ask questions. And we'll also be solving at the end some sample questions that will help you solve your assignment problems. Uh, so we'll begin now. Okay, so one of the first things that was covered in this week's lecture is the concept of conservation equations. So, if you have a quantity A which is conserved in a certain volume V, then change of A would imply that the quantity A, there is some influx or outflux through the surface bounding the volume V, right? So, if you're talking about the flux of a quantity A, that is basically given by rho times U, where rho is the volume density of the quantity A. So A per centimeter cube, let's say, would be rho. And the flux of A that goes out per unit area per unit time is given by A divided by the area times the time for the flow of this quantity A. And that is given by rho times U, where U is the velocity vector of this flow. Now, is this intuitively clear why this flux is rho times A, rho times U? This should be clear because you're considering, let's say, so rho is basically A times V, right? And since you're talking about the flux, the flow of this quantity A per unit area per unit time, all you have to do is, let's say, multiply by um, a fraction which is length by length, and you'll have your required quantity. Okay. Uh, and the conservation equation will be given by the rate of change of this full quantity A, which is given by the integral of this density rho over this full volume V, which is given by the integral over dV. That's your left hand side. So this tells you the rate of change of the quantity A in a volume V. And the right hand side gives you the flux of the quantity through the surface S. Now, since this should hold true for any volume V, the integrand must go to 0. If you pull this to the left hand side, the integrand must go to 0, and that gives you the equation for conservation of mass. And once again, this is in the Eulerian frame, where the Eulerian frame would be the frame of an observer who's the lab observer, who is actually observing the fluid particles move by. And if you have to write it in the Lagrangian frame, you know how the time derivatives in the Lagrangian frame is related to the partial time derivative and the divergences in the uh, Eulerian frame. And if you relate the two, you'll have the continuity equation in the Lagrangian frame. Now, what is the utility of writing the equation in Lagrangian frame? What can you conclude about a flow that's compressible or incompressible?
Divergence is zero.
Yes, but
Density is not changing.
that's right. That's right. Uh, so del rho del t, which is the change in the density that uh, an observer sitting on the fluid parcel would observe, that is zero. So that would tell you the divergence of u is zero. So this is just very quick recap of the things that has been covered. Just pause and just stop me and ask questions if you have any. Okay. And once again, if you have an incompressible flow, which means that del rho del T is zero. Sorry, is
Uh,
that a quick?
Actually, in the slides, have you, by mistake, have you replaced the multiplication sign by a subtraction sign here? Area minus time, because that doesn't make any sense.
Of course it does. In the slides, you probably have this term on the left-hand side.
No, 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 not this one. In the box, in the upper
So
left corner.
yeah, you have flux of A's.
Yeah, this is multiplication. This is supposed to stand for multiplication. Of course, area minus time does not make sense. This is supposed to stand for multiplication. Yeah, area time. Is that fine?
Yes, yes, yes. Now it's fine.
Okay, okay, thanks. Yeah, and so an incompressible fluid, an incompressible flow would be the same as taking divergence of u equals zero. Okay. Next, we have, just like we wrote a conservation equation for mass, we can write a conservation equation for momentum, which is nothing but F equals dp dt equals ma. And for that, we'll follow the procedure that was followed for conservation, writing a conservation equation for mass. We write down the momentum density. The momentum density would be rho u. And why is that? Because the momentum is mu. And if you want to find this quantity per unit volume, we'll just divide by v, and by v will give you rho. So the momentum density is rho u. The momentum flux is, by same arguments, this density times u. Now please stop me if this was not clear from the lectures.
Actually, in this case, is it some kind of a Hadamard product, which sir said in this lectures, like
This
outer
what
product?
this product is an outer product.
Yeah. So
That's it.
is it the Hadamard product,
What's a Hadamard product?
like the tensor product, which you say?
This is just an outer product. This is just an outer product with the components. You know what the components are. If u
So
is
I'm asking for the
I'm
notation
hearing.
of this one because it looks too vague, right?
this, what's vague about this? It's a 2 cross 2 matrix. If you write u as u1, u2, u3,
Yes.
I'm
then
hearing Hanneman product for the first time too. So I'd be happy if he clears that out. But anyways, yeah.
I don't think that's relevant here, and I don't think we need to worry too much about it. But just keep one thing in mind that this is not a scalar product. This is not a this is not a scalar. This is not a scalar. Okay, this is not a number. It's some sort of a matrix, some sort of a 3 cross 3 matrix. If this U is a 3 vector, is that fine?
Yes, that was fine. Means I was just asking if there is any special notation for this,
It's
because
a
there is
tensor. It transforms like a tensor.
no, like u and u means in between that there must be some sign, right? It cannot be a dot or a cross. That's for sure. But I'm just asking for that one. I know it's
See, it's a
not.
notational. If it's a notational thing for you in that case.
Yes,
Uh,
yes.
just look at U as the outer product of
So
U and
U
U.
outer product, you get U1, U2,
Okay,
U1,
okay,
U
fine, fine.
like
That's
help.
fine. That's fine.
That's
Okay. It's just notations. Do not worry about. Just know. Do not get too lost in the notations because we know what it is at the end of the day. It's an outer product. Okay. Okay. Cool. Um, so we know that the rate of change of momentum on any system is equal to the force applied on the system, right? So now if you want to consider the change in the momentum of all the fluid passes in a certain volume V, so this volume V must have lots of fluid passes, and we want to consider the change in the rate of change of momentum of all of these fluid passes. That must be equals to the force applied on it. But first, let's compute the rate of change of momentum of all of these fluid passes, and that must be due to intrinsic change, that is del T of the momentum of all the fluid passes, plus the flux through S, the momentum flux through X, through the surface bounding this volume V, which is given by this quantity. This is just analogous to the conservation equation we wrote for mass. Now my question is, should this be a plus sign or a minus sign? From the arguments of if the force applied on the system was zero, should this be a plus sign or a minus sign?
Hmm. But this is change in momentum.
Yeah,
Actually, net change should be equal to force applied, no?
absolutely. This would be equals to the force applied, and that we'll write down later on.
Okay.
But just from arguments of
Okay.
what would
So
have
you.
happened if the force applied was zero,
So
can we, how do we determine whether this will be plus or minus?
yeah. So you're writing u dot ds. So ds is usually outward normal. So if that
Hmm.
net is positive,
It is the
then
outward normal, yeah.
so if say the net is positive, u dot n like full integral is positive, then the it is going out, so it will be negative. So it should be negative over there.
No, no, we don't determine it that way. So I'll tell you and just let me know
Okay.
if you agree with this.
So,
This entire quantity, as you correctly pointed out, is going outwards. So this is the flux of the fluid parcels carrying some momentum going outwards, right? And what would happen if there was no force applied on the system? This should be equals to zero, right? So
mhm.
del T of this net P should have been plus or minus the flux through S, right? But the flux through S is positive. It's going out. The fluid parcels are carrying momentum out of this volume, right? What should that mean in the context of the rate of change of momentum? It should decrease.
Yeah.
That's correct.
Yeah.
Which means that this quantity on the right hand side would come with a negative sign. Because if this is positive, if the flux is positive, then the volume V loses momentum,
Correct.
right? So this quantity on the right hand side comes with a positive negative sign. So this should be plus.
Yeah.
Do you guys agree? Let me know.
Uh, can you
Can you come again?
means can you just explain this once again? Just
Sure. So if you just have these two terms, how will you know? Okay, we have said that the change in the momentum in this whole volume will be due to two things. One is because of intrinsic change. Two, because we have an influx or outflux of momentum through the surface bounding the volume V. Now, once we write down these two terms, how do we know that the net change in momentum dp dt is going to be this plus this or this minus this? Right? So all I'm saying is if there was no force being applied on all of these fluid parcels in the volume V, then this plus or minus this term plus or minus this term would be zero. Now, if the fluid parcels are carrying, if there's an outflux of fluid parcels, right, and the outflux sign of the outflux will be positive because the direction of the outward normal to the surface is positive. If there's outflux of momentum through this volume, then the volume V loses momentum density, right? So del T will be negative. If it were gaining momentum, it would be positive, right? That's why this has to come with a plus sign.
okay.
Okay?
Mhm.
Okay, good, very good. So if you apply divergence theorem on this will be converted to a volume integral with divergence acting on this quantity, right? And once you have dv on both sides, you can add these two terms and get this integrand. Okay. Next, we have to now compute the forces that are acting on a fluid. And let's say that there are two types of forces acting on the fluid. You have to, of course, treat body forces and surface forces differently. So let's say one of the body forces that's acting on this volume V is gravity. And let's say some pressure P. And the way the pressure tensor is defined and related to the surface forces is via this. So if I's were all of the surface forces acting and they were acting on the surface AJ, then PIJ is a tensor that tells you how it is the uh, how the forces act on all of these surfaces, right? So what one can do is one can rewrite this term as this. You guys can see my cursor, right? This is visible, the red thing.
Yes.
Okay. Uh, and then we end up with such an expression. Okay. So now all that's left to do is equate these two, and we get the conservation of momentum equation. Okay. Now there was an exercise that was not completely done in the lecture, so I thought it's worthwhile to do it here. Uh, This is quite a complicated equation. You have these tensors over here, and uh, this divergence acting on this, and so on and so forth. So there is this very simplified version of this conservation equation, which is the Euler equation, and the exercise was to show that for an inviscid fluid where the viscosity is zero, this equation simplifies to this equation. So we'll just do this very quickly once so that we know how to get the Euler equation from the general momentum conservation equation. Okay, uh, so what one does, and since, okay, so we'll now get to simplifying this equation. First term, we have del D acting on rho of u. And of course, this first acts on rho to give you this term, and then it acts on u to give you this term. Now, from the mass conservation equation in the Eulerian frame, you will remember that del rho del T was minus of divergence of rho u. So this term simplifies to this term, right? Now, things will get a little easier if we work with component notation. So we'll note this term as this and this. Let me know if this is fine. Is this clear? Is this clear? So you know that divergence acting on a vector u is given by this term, del xj, del xj of uj,
Yes.
right? Now the divergence will first act on rho to give you this, and then it will act on u to give you this.
Okay.
Next thing we'll write in component notation is this term, okay, where this grad operator will first act on rho to give you this, and UUs will be pulled out in this notation. Secondly, rho will be pulled out, and the grad operator will act on UU to give you this. Now notice that the G indices contract, and this equation are equations for the index I. J's are summed over. Okay, if there's still some confusion, we can come back to it. Okay, now there's some cancellation going on because this term cancels with this term, right? So we are left with this term, and this term, which we write in the left-hand side as this. And the right-hand side in component notation is given by this plus this. Is this fine? Is this fine?
Yes, ma'am.
Okay, okay, thanks. Now, for fluids which have zero viscosity, for ideal fluids, as was discussed in the lectures, in the pressure tensor, only the diagonal elements are non-zero. The off-diagonal elements are zero. Right? There is a result of the fact that if there is no viscosity, there will be no differential velocities in the profile for the fluid flow. So your pressure tensor will start looking like this, where only the diagonal elements are non-zero. The diagonal elements are zero. I hope this point was clear from the lectures. And if
What
that is
was
the
small p?
small p is just what I call the diagonal elements.
Okay.
Okay.
That's the pressure, no?
Yeah. Yeah. I mean,
Okay,
this
okay,
is the
okay.
pressure tensor.
Yeah,
I mean,
okay,
this is the
okay,
pressure
okay.
tensor.
Yeah,
Yeah.
yeah, yeah, got it. Okay, okay.
Okay. In that case, this becomes del del xi of p because I have a delta ij that turns the j label as I. Okay. And once again, I can actually act the del del xj operator on ui uj to give me these two terms. And then I'll see that this term and this term cancels. In which case I'm left with this, and in vector notation, going back from the component notation to the vector notation, this is nothing but rho of del u del t, and this is nothing but u. Do you guys agree that this term is basically this term? Okay, I'm hoping it's a yes. In that case, this is the equation that I get. And throughout this process, I've only assumed that I've only worked with a simplifying assumption that my fluid has zero viscosity, and I get the simplified form for Euler equation. Now I have a question for you guys. Is this equation valid for compressible flows?
No, because here you are taking this row out of the this thing del del t. Means you're treating this as a
That's
constant.
not true because, that's not completely true. That is because I have considered the del del t of rho term.
Okay, okay.
Okay. And one more thing is del rho del t is not the condition, del rho del t equals 0 is not the condition for incompressibility. D rho dt is. Thanks for pointing this out. It's an important point. D rho dt is.
Okay, means the
Compressibility
Lagrangian
or,
derivative.
huh?
The Lagrangian derivative you're talking about.
That's right. That's
Okay.
right. That's right. Compressibility will be concluded by an observer sitting on the fluid parcel. Okay, so once again, is Euler equation valid for compressible flows?
Yes, it should be, no?
That's right. That's right. Where have we assumed the condition for compressibility? Nowhere. So this should be valid for compressible flows. Thank you. Thank you. The only thing we have to keep in mind while using this equation is that it holds for ideal fluids. We have used the simplified assumption of inviscid flows. Okay? All right. Uh, okay, so just a few term dropping. First term is the incompressible flows, where we have seen that this is d rho dt equals 0, which is the same as divergence of u equals 0. The second type of flow one can have is irrotational flows, where the curl of the velocity vector is 0. Uh, and of course, this we related to the idea of a fluid being inviscid, of the flow being inviscid. That if a fluid has viscosity non-zero, then then the flow of the fluid has to be rotational, just because of the uh, differences in the velocity vectors and the velocity gradient being non-zero, right? Uh, so if you see that for a particular flow, the curl is zero, that the flow is irrotational, then you know that the fluid has to have zero viscosity. Now my question is, if you know you're working with ideal fluids, so is the vice versa true? That if you're working with ideal fluids, do you know that you have an irrotational flow?
I think the answer is no, because like if I have a if I have a flow of a viscous fluid in a pipe with
Hmm.
some diameter, then
Hmm.
the torque from both the ends will cancel out, and hence the
No, no, no. I'm not now. I'm not talking about viscous fluids. I'm just talking about a fluid that is ideal, zero viscosity. So now I want to know whether uh, any sort of flow that I'm considering for an ideal fluid has to be rotational. Is it
yes.
not possible to have uh, uh, rotational flows with ideal fluids? That
Yeah.
is my
So
question.
I mean, I have kind of an answer. Please let me know if that is the right way to think. So what you're trying to say is, if it is inviscid, so essentially your stress will become only the diagonal term, like the pressure term. Okay.
Mm-hmm,
And what we're
mm-hmm.
trying to say is the continuity equation and the momentum equation. The U has to follow a solution such that such that del cross V is equal to zero.
Yeah,
So
is that
is that
true?
a way to go about it, or how would you actually? That's what I'm thinking. It's a huge question
Yes, yes,
actually.
yes. You're
So I
absolutely
don't
right.
know
You're
if you
absolutely
should
right.
answer me here. Yeah.
You're absolutely right. So the only definition for inviscid flow that we have dropped up until now is regarding the off-diagonal elements of the pressure tensor. You're absolutely right. We have said nothing about a flow. We have not imposed any other condition for inviscid flows. Now, is that sufficient for us to claim that the flow of such a fluid has to be irrotational? The answer is no. Thank you for your participation. That's great that we have this discussion. The answer is
Thank
no.
you. Yeah. Thank you.
That the answer is no. That's because you can have other sorts of forces and that can introduce rotationality. So it's not. It is true that if you see that a, a flow is irrotational, then it cannot be a viscous fluid because viscous fluid will most certainly have rotational flows. But it's not true that if you have ideal fluids, then you will always have irrotational flows. That is not true. So this one must keep in mind.
So can we maybe kind of make an argument like let us say initial flow such that it is rotational, like U is rotational. There's no inviscid, like there's no shear stress involved in it. So can we? So if there is no viscosity, so the
Mhm.
rotational has to be like it should be constant, right? The vorticity has to be constant because there's no viscosity involved. Do you get me?
Vorticity being constant or non-constant. We'll come to the dynamical equation of motion for vorticity later on. Uh,
Okay.
but but all I'm trying to say is, if a fluid is viscous, it has to have a rotational flow. That is
Okay.
from this diagram. That is
Okay.
from this simple argument. If a fluid is viscous, it has to have rotational flow. If it is irrotational, it cannot be a viscous fluid. It has to be an ideal fluid. But
Okay.
if it is an ideal fluid, it's not necessary that the flow has to be rotational. It can be rotational as well. That's it.
Cool. Yeah.
Okay, thanks. Is it not clear to anyone? Please feel free to stop me. We can have this, we have enough time. We can discuss this. Okay, so let's suppose we have a flow that's incompressible as well as irrotational, right? So if a flow is irrotational, what we can do is we can define the fluid velocity vector as the gradient of some scalar function because curl of a gradient is always zero, right? And if you have u as some gradient of some scalar function and the divergence of this u is zero, then what the scalar function phi essentially satisfies is Laplace's equation.
What is this potential actually called?
It's some scalar potential, and such
Eh,
flows are called potential flows. Okay,
Okay, so
so if
it has got no name.
it's some scalar potential.
Okay, okay.
Okay,
There's just like age has no
call
name
it flow
in
potential. Maybe call it flow potential
okay.
because these flows are called potential flows because you can write the velocity vector as the gradient of some scalar potential. Okay, okay. Now the thing about Laplace's equation is there was one comment made in the lectures that such scalar such functions are featureless. What that that means is that there are no features in the profile of phi. So if you plot phi spatially, you will see that there are no features, the features being a minima or a maxima or anything. And that has to imply that phi at every point in x has to be the average of the values of phi around that point. Now, just so that we know why that's true from Laplace's equation, one can, so in the lectures it was argued by discretizing space into points, and you guys were asked to prove that if that if the value of this function phi, which I'm calling v over here, uh, at the points I minus 1, I and I plus 1 is vi minus 1, vi and vi plus 1, then you can show that this condition would mean that v at I is the average of the values of v at I minus 1 and I plus 1. This will come from this equation. Okay. Now, have you guys tried proving this? Have you guys tried this out? Yes, no, maybe. Tried but got stuck. Anything?
No, not me. Anyways.
Okay. Go back, try it out. Try it out. If you guys can't see it right away, then maybe post a question on the forum, or we can also take it up in the next week's lecture. But another way to see this would be, let's say you consider a point x and you consider a point very close to it, x plus a, right? This is x and this is x plus a. So a is a very small number as compared to x. So you tailor expand the function v at x plus a about values of v at x. And this is what the expansion will look like. You do the same thing. Oh, I'm so sorry. This is supposed to be minus. I'll correct it when I upload the slides. Sorry. You do the same at x minus a, and this is what you get, right? Now, since a is a very small number, we'll limit to a cube terms because a is small. So as you take higher and higher powers of a, they'll become smaller and smaller, right? And since d2v dx2 is 0 via Laplace's equation, these terms drop out, these terms cancel plus or minus. So all you're left with is if you add this and this, you'll get Vx as the average of V at x plus a and at x minus a. That's all it means for V to be featureless, which means that V cannot have a maxima or a minima at any point in space. Now, why is that? If V has to be an average of points neighboring it, why can't V be a maxima and minima? I think it should be clear, right? It can't be a maximum because then it can't be the average of 2 points. Is that intuitively clear?
Yes.
Okay, thank you. Okay, so phi, that's what it means for phi to be featureless. Okay, I hope these comments from the lectures were clear. Okay, now remember that we for 2D flows we could write u as some curl of some scalar function z cap. Now for irrotational flows, it's possible to prove that psi also satisfies Laplace's equation. Now, how would one start proving that? One would take curl of u, where u is already defined like this. So one would basically get curl of psi at z cap. Now curl of a vector is gradient of divergence of the vector plus Laplacian of that vector. But can you guys tell me what this will be? And remember, psi is a two-dimensional
0.
flow. Thank you. That is because psi is a two-dimensional flow. So the divergence, and unfortunately, psi comes with a z cap. So the divergence only the del del z acts on psi, but psi is a function of x and y. So this is just 0, which gives you your answer that Laplacian of psi should be 0. So psi also satisfies Laplace's equation for irrotational flows. Is that fine?
Yes, ma'am.
Okay. Thanks a lot. All right. Now let's try to say a few things about the energy content of the volume we are considering. Let's once again start with Euler equation, and let me remind you, it only uh, takes in the assumption that the fluid has zero viscosity. Euler equation was the simplified version of the momentum conservation equation, and the simplifying assumption we used was that the fluid has zero viscosity. Okay, and this is Euler's equation. Now we'll put in one more assumption. We'll put in one more simplifying approximation that we're dealing with steady flows. The definition of steady flows is that del U del T is equals to zero. So what that means is, for an Eulerian observer would see that the velocity profile does not change with respect to time. That's a steady flow. Okay. And if we work with steady flow approximation, then this term drops off. And if you use some vector identity on this, the left-hand side turns out to be this, with rho taken to the right-hand side, cancelling rho in the term g, and just turning up in the denominator of this term. Okay. All right. Now, this equation, let us integrate it along dl, where dl is a small line segment along the fluid velocity, which is also the streamline. So we want to integrate this along the streamline, right? And if we do that, this term just becomes u squared by 2, right? Now, what about this term? Since we are dealing with non-viscous fluids, can we write del curl of u equals 0?
Yes, because it is irrotational.
No, see, that's the discussion we just had, that if you're dealing with non-viscous fluids, if you see that curl of u is 0, then you know that the fluid cannot be non-viscous, because viscosity always introduces rotationality, always gives you a rotational flow. But if you have an ideal fluid, that can have non-zero curl.
Okay.
Okay, good. So I hope it's clear now that you cannot claim curl of U is 0 just because you're working with inviscid fluids. Okay, right?
Yes.
So this term stays and it's not 0. And uh, and we also note that this entire vector is actually perpendicular to U, right? Because it's U cross product of some vector A. Once you're taking cross product of a vector, the resultant vector has to be perpendicular to U, right? But we know that dl, that is the line segment along which we're integrating this entire equation, is actually parallel to u, right? And you're taking dl dot product of this entire vector, which is perpendicular to dl. So what will it be? It will be 0. Agree? Do you guys understand?
Yes.
Okay, okay.
Can you
Uh,
repeat? Clear?
right. So this entire vector is perpendicular to u. Do you agree?
Okay.
Do you agree? Do you agree? Let me know if it's not clear. That is because this is some vector. I don't care what vector this is. But once you're taking the cross product of two vectors, the resultant vector, which is this full vector, has to be perpendicular to both u and a, right?
Yes, ma'am.
Right? So this full vector is actually perpendicular to u. Let me call this full vector b. Okay? Now when I integrate this along streamline, I'll be taking a small length element along the velocity flow. This dl is parallel to u, and I'm taking its dot product with a term which is perpendicular to u. So what will this dot product be?
0.
0. I'm taking dot product of two perpendicular vectors. So they'll have to be 0. Correct?
Yes, ma'am, got it.
Okay, thanks. Is it still not clear to somebody? Okay. Uh, so this term will give you integration over dp by rho. This term will give you integration dp by rho, and this term will give you just phi. And of course, since you have not set limits, you'll have some integration constant popping out. But the interesting thing is this entire thing becomes constant. And this equation, if you write it in the more popular sense of P by rho, which will be true if the density profile were not dependent on the pressure. So if you're working in, let's say, small pressure ranges where the density really is independent of throughout the full range of the pressure you're working with, then this rho just comes out of this integration, and you write this dp as some p. Then this is this popular Bernoulli's equation that you guys must have, let's say, studied in your class 11th, 12th, right? Right. So this just tells you that the energy content, which would be, let's say, due to the gravitational potential, due to the pressure applied, because pressure applied also gives the system some energy, and that is to be expected because what this was some sort of FTL. That's
Okay, so
exactly what.
is the gravitational potential buried inside this phi?
Yes, I rewrote G as
But how?
that. This is how.
Uh,
This is some gravitational potential.
okay.
And I wrote G as some minus grad of phi.
Okay, but so this phi is not the same as that the other potential.
Absolutely not. No.
Okay, so I got confused because of this one.
Yeah. No. Understand the context. I mean, just because they're same symbols, do not get confused. Okay. I just rewrote G as this. Okay.
Okay.
Okay. So this gives you a sense of the energy of the fluid parcels. And as the fluid parcels move along the streamlines, what is the energy? They're constant. Things like that. Okay. And remember that you're working with steady flow and zero viscosity, zero viscosity, no dissipation, and steady flows. Now, my question is, does this equation hold for compressible flows? Does Bernoulli's equation hold for compressible flows?
No,
Sorry, was that an answer?
no,
Okay, so where have we used the assumption of simplifying assumption of a flow being incompressible? We haven't, right? We were working with Euler's equation, and simplifying approximation we used to derive Euler's equation is that the flow should have zero viscosity. And then we use the simplifying assumption of steady flow. But we nowhere have we ever mentioned any constraint of the flow uh, uh, being incompressible. Do you agree? So I would urge you to once again watch the lectures or go through the lecture notes and argue with yourselves that have we ever used the constraint of incompressibility or compressibility in deriving this Bernoulli's equation?
Okay, so the statement which will of the Bernoulli's theorem which we learned in school is actually not fully correct.
Okay, so what did you learn?
Of this incompressible, this clause was there in the definition.
It was there.
Yes, it
So
was there.
I would like you to argue that where have we used compressibility in deriving? Okay, think about it. Think about it. Is that fine?
Yes.
Okay. All right. So one of the last things that was done in this week's lecture was deriving a dynamical equation for the vorticity. That gives you the how the rate of that gives you the change of vorticity with time, right? And so we start with Euler's equation. We use a vector identity and rewrite this as this, right? Now, since the vorticity is the curl of the velocity vector, we take the curl of this entire equation. The first term gives you this. What will the second term give you? Understand that the second term is a total gradient term. So what will the curl of the second term give you?
0.
Great. Because what's the curl of a gradient? It's 0, right? Similarly, for this term and this term, since del p and del rho, these are also total gradient terms, when curl acts on this and this, gives you 0. So curl will act on this 1 by rho on this full term and give you this, this, and curl acting on this will give you this. Is it clear? So now you know how to show this. Any questions?
Can you repeat the right hand side part alone?
The right hand side part, so the curl will act on this full term. There are two terms. One is this, second one is this. Product rule. Product rule. Okay. So when this grad operator acts on 1 by rho, you get this term. And when operator acts on del p, you get 0. Why? Because it's a total gradient term. Similarly, curl acting on a gradient of phi is going to give you 0 because curl of a gradient is 0. Is that clear?
Yes, ma'am.
Okay, good, very good. And since this is vorticity, this is curl of u, so this is vorticity. This term is u cross omega, and you're simply taking curl of u cross omega. So this is an equation that tells you how vorticity changes with time. Okay. Okay. So one of the last things was a statement that was made that the pressure for barotropic fluids can be written as a function of the density, which means that del rho and del p are parallel to each other. Now, is it clear why that's true?
Yes, ma'am.
Okay, just for the sake of everyone agreeing to the statement, del of p is del of some function of rho, and this gradient of this function is going
Uh,
to give.
One thing I want to ask, like, since I missed watching the last lecture, so what is the meaning of barotropic fluid actually?
Yeah, barotropic fluid are just fluids where the pressure can be given by some function of rho. Or in other words, your density is just a function of the pressure applied to the fluid.
Okay, so is there any
So for
counterexample?
yeah. So for fluids, what is it called? Barocentric, yeah. So fluids that are not barotropic, they're probably called barocentric or something. I urge you to look it up. For those fluids, the density is not a function of pressure alone. It can depend on other factors as well.
Okay.
So I was just want to ask one question because it seems pressure is function of density. If you know anything like weakly compressible flows, I hope, I mean, if you know them. So usually we relate pressure with like Tate equation. Do you know
Yeah.
any of those stuff? So there actually we relate pressure with the density. So does barotropic mean like the flow is incompressible, or do we consider those conditions as well? Because we usually say, okay, let's not consider it as incompressible. Let's make it weakly compressible, and relate pressure to the little changes of density, and we call we bring on rate equation and all those stuff.
So I would like to understand why do we need to get rid of or weaken the constraint of the fluid being completely incompressible for us to relate the pressure of a fluid to the density of the fluid?
Okay.
Because to me it feels like incompressibility would just is just a statement of this, right?
Yes.
Yeah.
Yes.
So this is more or less like in gases you mention equation in not just in gases in yeah in fluids you mention equation of state, right?
No.
If you remember,
Okay.
you relate the pressure and the density of on a fluid.
Yeah.
Yeah. So if you
No.
can do that, if you can write an equation of state, then it's a barotropic fluid.
Yes.
Otherwise,
Yes.
if there are more parameters involved, if the density of the fluid does not just depend on the pressure, it depends on more terms.
Correct. This is very true. So I just want to ask, like, if any of the audience or the instructor herself, if she has experience with computational fluid dynamics, so what we usually do is we consider it as incompressible, and we eventually
Hmm.
solve the pressure Poisson equation to get the pressure right. Q.
Okay.
So there you don't relate pressure with density. So there you don't have this pressure density relationship. But in terms of
Okay. Okay.
computational fluid point of view, I'm just completely
Okay.
different
Okay.
point of view
Okay.
trying to discuss,
You're okay. I understand. You're talking.
right? But if you a numerical technique called smoother particle hydrodynamics or some like particle methods, so there we relate pressure with density rather than solving pressure Poisson equation. So I was coming from that point of view, understanding, like think
Okay.
like asking. I have a doubt, like question and doubt.
Okay. Okay.
Uh,
Okay.
but
Yeah.
anyways, yeah.
Thanks for your comments. Yeah. I guess you guys have more experience. You must have more experience with since you I think work in computational fluid
Yeah.
dynamics.
So,
Uh, but yeah, thanks for the comments. Yeah.
I get it. I get it. Yeah, I
Yeah.
get your answer. Yeah, sure. Let's continue.
Okay. Okay. Yeah. So as I was saying, that's simply because gradient. Oh yeah. So gradient of p and gradient of rho would be parallel to each other. Why is that? Because gradient of p, which is now a function of rho, will be written as dft rho times this entire thing, and this entire thing is nothing but gradient of rho. So it's just some factor times the vector, which is grad rho. So of course, grad p and grad rho are parallel to each other. These two vectors are related by just this uh, scale of this factor over here. Okay, which is why for these fluids this term drops out, and you get this very simple equation for uh, the vorticity of the fluid. Okay, we'll move on to sample assignment problems, if that's fine by everyone. Okay, so the first question is let's consider fluid flowing through a pipe. Uh, Given that you can write U as some curl of psi, let's say z cap, and these are 2D flows, right? So U is in the xy plane, and curl of z will take you to a vector in the xy plane. So you have to choose which of these statements are true. Can you write divergence of U equals 0?
Can you repeat, please? Sorry.
If you can write the velocity vector as curl of some vector psi z, if you can write the velocity as a curl, then
Velocity.
can you write the divergence of velocity as 0?
Okay.
Yes.
Yes, this is simple vector
Mathematics.
algebra.
Okay.
Yeah, absolutely. Divergence of a curl is 0.
Correct. Yeah.
Correct? Okay. So we have option A is correct. Okay, option B is a Lagrangian observer will detect changes in fluid density such as compressions and rarefactions. Is that true?
No,
Why is that?
because because of the first condition, this is the condition for incompressibility.
Absolutely. Thank you. Thank you. This is not true because compressibility tells you that divergence of U is 0. So you cannot possibly observe compressions and rarefactions. Okay. Uh, okay. Streamlines, so option C and D are streamlines in the fluid can intersect each other, or the
No,
streamlines in the fluid have always to be parallel to each other.
always parallel.
Absolutely. These are what you would expect to be smooth flows. Streamlines do not ever intersect in smooth flows. Okay, you will learn more about flows where the streamlines intersect each other and so on. These things happen, but these are nice flows, and you would expect streamlines to be parallel to each other.
Okay, but
Okay,
if the streamlines intersect in if so-called turbulent flows, if the streamline if they intersect, then it will have two velocities in one instant, which is impossible. How
that's
does that happen?
turbulence. That's turbulence. That is turbulence. Yeah,
No, but
you'll
how can you have two
probably.
velocities at one point of time?
So it won't. That's the point of, like, you can't define the velocity at that point, right? So that's the turbulent flow. It can go either way,
Okay, so is it
right? Turbulent flows are, it's we should not wave our hand and say that okay, this is what turbulent flows mean. It's much more sure, it's much more complicated than that. But let's wait till we have further discussion or more material from the lectures. But for now, we know that this is a very nice flow, and we don't expect streamlines for nice flows to intersect. They would be parallel to each other. Okay.
okay? Mhm.
Okay. Cool. So the correct option is A and D. Moving on to the second problem. So there is something called the Boussinesq approximation. I hope I'm pronouncing it correctly. Uh, you have four options. Whether this approximation is related to the mass conservation, the energy conservation, or incompressibility, or whether the situations, or whether this approximation is valid in situations where you can neglect variations in the density in terms which have G.
C and D are the correct answers.
Correct, correct.
Mhm.
This is just from this is not something. This is just an approximation that was just
Why
mentioned in the
why
lectures.
do you call the whatever approximation? Can he answer that? Because I don't know.
Oh, can you repeat your question?
Yeah. So why are those two options called Bosniak approximations?
This is just
I
an
don't know.
approximation that one would. So if you remember, not if you remember, of course, once you have an equation of motion for a flow,
Okay.
there are lots of terms, and with fluids, tends to be uh, it tends to involve a lot of complicated terms, and one would like to drop out a few terms if possible, right?
Okay.
Now, if you remember, the Boussinesq approximation told you that if you're dealing with flows where, let's say, so if I remember correctly, it was something like this. Let's say you have a gravitationally stratified fluid, right? Where the e-folding length of the density is, let's say, L. And what does e-folding length mean? That in a distance L, the density can either become E rho or rho by E. That's what e-folding lengths mean. That if you go along this direction, of course, gravity is acting along this direction. So if you go along this direction, the density will become rho by E in a distance L, right? And if you're considering flows uh, that are much smaller than L, then the fluid parcels don't actually notice this change in density variation because if the scale of the flow is much smaller than the folding length of the density profile. Okay, and
Okay.
if that's true, we can work with a simplifying approximation that will, let's just ignore terms that have density variations in them,
Mhm.
unless they come with G,
Okay.
because G is what introduces this stratification in the first place. So
Okay.
G is what, in some sense, sets the scale for this L. So density variations with G might be relevant. Okay.
Okay.
Do not worry too much. So I will. This is what I'll advise. Do not worry too much about this approximation because you probably won't be using it anyway. This is just to tell you that when one works with, so you work with computational fluid dynamics, right? So when one works with complicated equations of motions for fluid, one would like to drop out a few terms whenever possible.
Yeah.
One would like to simplify their lives. It's very complicated anyway, right?
Yes. Yes.
So if you can
Yes.
drop a few terms, do it. That's that. This is just one of the approximations one can use in a given
Yeah.
situation. Okay,
Cool.
cool. Uh, okay, moving on to the next problem. Um Choose the correct statements. Potential flows are irrotational. Okay, let me remind you what potential flows are. I just mentioned it. Potential flows are when you can write the velocity vector as some gradient of some scalar function, some scalar potential. These are potential flows. Now, potential flows are irrotational. Is it true?
So if you do curl of this, it should be equal to zero.
Yeah, yeah. Thank you. That's right. So
Is
A is
it?
true.
I don't know. Okay.
A is true. So
Yes.
it's good to remember. I think it's when working with fluid dynamics and these equations, it's always good to remember what will be zero if you take, like, let's say curl of gradient or gradient of curl or divergence of curl or curl of divergence. Which of these is zero? It's good to remember because then because you might miss a few things. You might miss a few cancellations here and there when simplifying equations or working things through. Okay.
Yeah.
Okay. Uh, All right. Viscous flows can be described using a scalar velocity potential. Is this true?
Hmm. So we discussed the viscous potential is not irrotational. Okay.
Viscous flows are
The-
always rotational.
yeah. So according to
Yeah,
logic A, so it actually B is wrong. If A is right, B is wrong.
absolutely. Absolutely. If A is
That's
right,
how
B
I'm
is wrong.
going.
Absolutely. Correct. Thanks. That's a good way to think about it. If A is right, B is wrong. Right. Uh, and see,
I mean B.
a smooth sphere moving through a perfectly invisible fluid will feel no drag.
Yes.
True.
Absolutely. It's a non-viscous fluid. What will provide the drag? Nothing. It'll move smoothly. Okay. So the correct options are A and C. Okay, moving on to the next question. Consider steady irrotational flow of an incompressible fluid.
Okay.
And there are no external forces acting on the system.
Mm-hmm.
Now you have to say which of these statements are right. One can define a velocity potential for the system. Is this true?
Yes.
That's right. That's right. Right? Okay, let me since this involves a little bit of mathematics, let me so one can define a velocity potential for the system. That's true. Why is that true? Why is it true? Why can I write u as some this?
Because the curl of u is zero, right?
Correct, correct. One cannot define a stream function for the system. That's not true. You can define a stream function for the system. Okay. Uh, two of the octagonal terms of pressure tensor are non-zero. Is this true?
No,
So,
because everything is assumed to be ideal. So on
right. You are working with an irrotational flow, which means the fluid has no viscosity, which means that all of the octagonal terms are zero. Correct. Thank you. The last option is whether this is zero. Now, the way to check this is actually by looking at the momentum conservation equation, which is this. Now, this is the momentum conservation equation under no external force in all its glory, without the simplifying approximation of steady flow and so on. Okay. Now, what one would do is act this operator on rho u to give you these two terms, and then act the divergence operator on this term to give you these two terms. This left hand side is the dp dt, the rate of change of momentum. The right hand side was the force, which in this case is zero. Okay, is that fine? Okay, so if you look at this term and this term, you will see that it's nothing but this term. This is how the time derivative in the Lagrangian frame was related to the derivatives or the rates of changes in the Eulerian frame. You can combine these two terms to write this. And since you're working with a steady flow, this term drops off, right? So you have this plus this. Now this term is also 0. Why is that?
Incompressible.
Absolutely. Thank you so much. This is incompressible. So this is 0, which means this is 0. What does this mean for option C? That is not true. Thanks a lot. Thanks a lot. Okay. Last question. Uh, the Bernoulli parameter is this. Okay, thanks a lot. The other parameters carry the usual meanings. Now you have to pick the correct statement. The Bernoulli parameter is conserved only if divergence of u is 0. Is this true?
No.
Correct. Thanks a lot. Why is that?
We have already discussed that because we have nowhere we have made this approximation that it is incompressible.
Absolutely. 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 That's right. Okay. Now the Bernoulli parameter is conserved only if Laplacian of phi is 0. So remember that Laplacian of phi was 0. This held true. Now this phi and this phi are different. Remember, this is the gravitational potential and this is the potential flow, the scalar potential that you can write u as gradient of phi. Now if Laplacian of phi is 0, only then the Bernoulli parameter is conserved. Is this true? Remember that this was satisfied if you had arotational plus incompressible flow. Do you remember? Arotational plus incompressible. Once you have these two conditions in place, only then phi satisfies Laplace's equation. Okay. So which means that option B is not true. Now, is this not clear to anyone? Okay, I hope that is clear. Uh, now, the Bernoulli parameter is conserved only if phi is a conservative potential. This phi is a conservative potential. Is this true or not? Random guesses? Anything?
What
Not
is
true.
meant by
Why?
conservative potential? Because potential is always defined for a conservative thing.
Absolutely. Absolutely. And also, it's not true. That's right. Anyway, if you have something that's not conserved, E is not going to be conserved if you have dissipative forces. Plus, you can't even define phi if the force that was acting on it was not a conservative force. Okay, thank you. The last option D, Bernoulli parameter is conserved only if del U del T is positive. We made no such claims. We made no such claims. So that's why the only correct option is C. Okay, so this concludes our live session today. Uh, if anyone has any questions, you can ask or you're free to leave.
Can you explain that outer product?
What about it?
I mean, just the logic.
Shasta logic. Okay, so I'll tell you what the logic is. Okay. Uh, so the momentum density turns out to be a vector because momentum is a vector. So the density, of course, is a vector. Now you're dealing with the flow of a vector through a surface, right? Now, if this were a scalar quantity, the flux of the scalar quantity would be a vector, correct?
Yes, ma'am.
Now you're dealing with the flux of a vector quantity. You want to define the rate of change of this quantity through unit area. That's what flux is. But this quantity is now a vector. So this flux, you do not expect it to be a vector or a scalar quantity. You expect it to be a tensor. More so because we just noticed that if you're working with any quantity A, then the flux of that quantity is going to be the volume density of that quantity times U. We do the exact same thing over here. We work with the momentum density rho U, right? And we multiply it with the fluid velocity vector U. But what sort of product is this going to be? It can't give you a scalar or a vector because now you're looking at the flux of a vector quantity, so it's a tensor. It's an outer product.
Okay, ma'am.
Okay, guys, I'll thank you for joining. I'll stop the recording now and I'll wait for a few more minutes in case any of you have any questions.